Dear audience, my name is Tekla Tóth. I am a second-year PhD student in computer vision at Tóth University. We present an automatic LiDAR-camera calibration method with a spherical target. This is the result of a cooperative work with my supervisor Levente Hajder and is based on some recent work from Zoltán Pusztai. Sensor calibration is a critical step in autonomous driving system, or in general, every sensor system where we would like to use many devices with different modularities simultaneously. If we combine the result of more sensors, we can get a more detailed understanding of the environment, and we can apply several computer vision methods more efficiently. However, multi-sensor input requires their relative view parameters, the position and the orientation. Calibration is based on either some properties of the actual environment, like edges, corner points, features and their descriptors, or a specific calibration target object. Planar board with a chessboard texture is the most popular choice for cameras due to its robustness. However, not only is the LiDAR data too sparse for precise edge estimation, but the checkerboard pattern is less visible to the sensors, leaving the LiDAR's precision in depth unexploited. In this particular case, we will calibrate one camera to one LiDAR sensor. We assume that the sensor's extrinsics are already calibrated. We aim to compute the translation vector and the rotation matrix between the sensors. We propose a fully automatic calibration pipeline which contains three main steps: sphere center estimation both from point clouds and images, and then the so-called relative pose estimation. In order to use a point pair registration algorithm for this pose estimation, we have to measure at least 4 sphere center point pairs. At the beginning, we apply one of our former published object recognition algorithm in the point cloud, which also estimates the radius of the sphere. This information is fed to the second novel part that estimates the sphere centers from the images. Note that the projection of a sphere in the image plane is a conic section, notably an ellipse, so at first we have to estimate the ellipse parameters. The sphere center and the radius are estimated from the LiDAR data with a fixed point iteration based on minimizing the least square problem on screen. The first part of the image processing is the ellipse detection. After applying the canny edge detection method, we approximate the projection of sphere contour with a circle to reduce the size of the in-layer point set of the RELSEC fitting method. Another criteria of the in-layer selection is that the edge should point toward to the tangent of the circle. A precise ellipse is fitted afterwards, which gives the coefficient of the equation of a conic section in the numerically stable normalized image coordinates of u hat and v hat. The coefficients can be expressed using the sphere center coordinates and the radius. This leads us to an overdetermined but numerically sensitive equation system which contains one more unknown parameter, the scaling factor alpha. Thus, after an initial estimation, the final result needs to be refined with the Levenberg-Marquardt algorithm. The pose estimation is solved by a point set registration method. The translation is eliminated by selecting the origin as the barycenters for the 2 point sets. The rotation matrix is obtained through the singular value decomposition of the matrix constructed by the sum product of the point pairs. The calibration process was tested in several setups: a photorealistic Carla simulation environment, Blender synthetic setup, and real sensors too. The result of the ellipse detection from camera images is visualized here for these different scenarios. These tables contain the mean error and the standard deviation of the synthetic test measurements for the sphere center estimation from the camera and the LiDAR. The optimal sphere center estimation from images reduces the mean error to be between 1 and 3 cm in our synthetic tests, even if the initial estimation gives 1 meter error on average. The distance error is influenced mostly by the depth values. This MeshLab project contains a real-world test example for the sphere center estimation in 3D point clouds. The orange inlier points were found automatically, and the reflected yellow sphere was generated with the estimated parameters. We tested 3 state-of-the-art methods against the proposed calibration process. The kitted toolbox calibrates with 4 chessboard textured boards, and the result has to be chosen from several offered options. The polygonal method needs at least 3 white boards, which are chosen manually from the point cloud. The box algorithm uses 3 perpendicular planes after the manually marked corner points in the image. We measured the translational and angular error of the calibration methods on synthetic tests. This slide shows these errors against varying Gaussian mean values. The proposed method outperforms the state-of-the-art methods under several mean noise values. In terms of standard deviation, our algorithm performs competitively too. In the real-world test, we calibrated a Velodyne VLP16 LiDAR to an iCube digital camera. We used a sphere with a radius of 13 cm. Our algorithm estimated it with 2% error. This figure illustrates the distances between the spheres and the sensors for our real-world tests. The comparison of the methods is done visually by reprojecting some part of the LiDAR point cloud back to the camera image using the estimated parameters of the methods. The scene containing the 5 boards can emphasize the errors at the edges very strictly. Thus, this red point set is reprojected to the images with the estimated extrinsic parameters of the proposed and concurrent methods too. If the extrinsic parameters are accurate, then the reprojected LiDAR points cover their corresponding pixel, otherwise the reprojections are shifted. The box calibration approximates the optimal result the best. Nonetheless, the proposed one still performs better than the others. In summary, we presented a fully automatic LiDAR camera calibration method. We validated and compared our method against the current state-of-the-art methods. In conclusion, our algorithm had better accuracy than the current semi-manual methods, whilst being fully automatic. Our method could be extended to any number of sensors using bundle adjustment in the further. The first step of our calibration process can be applied not only from LiDAR point clouds, but from the 3D output data of any devices. Hence, we will extend our setup with a depth camera too. Thank you for your attention. I'm happy to answer any questions.